Okay, so welcome back to the second lecture. He's gonna continue from yesterday, please.
Okay, thank you very much. So let me continue. Today, my goal is to explain the higher genus reconstruction formalism of Q and tau. So let me start first with the notion of a semi-simple Frobenius manifold. So suppose that we are given some Frobenius manifold M, so it's equipped with non-degenerate bilinear Frobenius pairing on the tangent bundle, Frobenius multiplication, unit vector field, Todor vector field. So this is a Frobenius manifold. Then let us give the following definition. A point T in M is said to be semi-simple. Semi-simple if there exist local coordinates they're called canonical coordinates. Let me denote them with U1, UN, near this point, such that the multiplication ddui dduj equals delta ij dduj. So delta ij is the Kronecker symbol. So in other words, our Frobenius algebra split into direct sum of one-dimensional algebras. And let us denote with MSS the set of all semi-simple points. Semi-simple. And then if this set is not empty, then M is called semi-simple. And it's called semi-simple, and the complement K equals M minus MSS is called the caustic. The caustic of M. And now let me make here some remarks. First, this caustic K could be either empty. So every point might happen to be a semi-simple. For example, this happens for the quantum homology of P1. So K is either empty or it is an analytic hypersurface. Hypersurface in M. And the second remark is that one can prove that a point is semi-simple if and only if the tangent space, it's an algebra, Frobenius algebra. If this Frobenius algebra does not have nilpotents, does not have nilpotent elements, i.e. it is a semi-simple Artin algebra. And in one direction it is obvious. So if you have a semi-simple point, that the statement that you don't have nilpotents, it's obvious. But in the opposite direction, it's the proof is a bit tricky. So you have to study what is called the analytic spectrum of the tangent sheaf. Anyways, but I'm not going to talk about this. So now suppose that we have a semi-simple point. So I want to introduce some notation that I want to use. So suppose that that we have a semi-simple point, and let us denote with U1, UN canonical coordinates. Coordinates with T1 up to Tn flat coordinates. Flat coordinates. First, one can see immediately using the Frobenius property that the Frobenius pairing in canonical coordinates is given by a diagonal matrix, and I'll write it in the following form. So the diagonal entries will be denoted with delta J. So these delta J's are some holomorphic functions defined in a neighborhood of this point T0 that do not vanish there. And then we define, so let us define several n by n matrices. So let me list them. So the first one would be denoted with psi. So the entries would be psi ai. Actually, the entries would be functions. So this matrix would be some kind of a normalized Jacobi matrix. For the change from flat to canonical coordinates. And actually, I'll try to stick to the following convention. I try to use indices ij and k when I work for quantities that are defined in canonical coordinates, and a, b, and c for things that are defined in flat coordinates. So G, this is just the matrix of the Frobenius pairing. In flat coordinates. Then we have AK. So this is a matrix, right? So this is the matrix of multiplication by the vector field ddtk, right? In flat coordinates. And finally, U is going to be the diagonal matrix, with the diagonal entries are the canonical coordinates. And let me give you actually precise definitions of the entries of these matrices. So psi ai, psi ai of t is defined to be square root of delta I dta dui. Right, so here the indices are between 1 and n. The matrix GAB, this is a constant matrix. It is the Frobenius pairing in flat coordinates. And then the matrix AK is defined by by the multiplication. I guess the definition here is here. Right. And then with this notation, then we can list the following properties of semi-simple Frobenius manifolds. So let me call it proposition 1. So the first property is that each canonical coordinate ui viewed as a function on the Frobenius manifold is a multi-valued analytic function on M minus K. So a priori, the canonical coordinates are defined only in a neighborhood of a semi-simple point. But the statement here is that if you take any global path in our Frobenius manifold that avoids the caustic, then the canonical coordinate would have an analytic continuation along this path.
I have a question.
Yes.
So when you say M subtract K, it's just M semi-simple, or what's the difference?
Where is the M? Sorry,
M minus
MS?
K. So you just write down M minus K.
Yeah, right.
M as
Yes.
semi-simple?
Yeah, it means semi, right. Okay,
M
so
semi-simple, okay.
Yeah, yes, I can make it. Okay. Then the second property is that in fact there exist canonical coordinates unique up to permutation such that the Euler vector field takes the form sum I from 1 to n ui ddui, and the unit vector field is just the sum ddui. Right, so in particular, if you take some closed loop in the complement of the caustic and you make analytic continuation, then this analytic continuation would only permute the canonical coordinates. Okay. So then the third property, well, this is something that I already listed, so maybe namely that the Frobenius pairing has this form, right? So here delta J, now thanks to the first property, delta J now is not only a locally defined function, but it's is a multi-valued analytic function on M without zeros, with no zeros. The fourth property is about this matrix psi. This was the normalized Jacobi matrix. So psi transpose is equal to G inverse. In my previous lecture, I had some transpose that I denoted with capital T. Here, this small t means usual transposition of matrices. Not with respect to the Frobenius pairing. The fifth property is let us define this. This is the connection matrix that actually enters in the structure connection or in the Dubrovin's connection. So if you write the Dubrovin's connection in flat coordinates, this would be actually the connection matrix. Then we have the following relation: psi1a psi is equal to differential of u. Right, so this psi diagonalizes the connection matrix, conjugation by psi. And the last property, this is a consequence essentially from the previous one, is that if you conjugate the operator of multiplication by the Euler vector field, this just becomes the diagonal matrix U. Right. So these are the basic properties. And let me again make a remark. Property 1 is hard to prove. It's hard to prove. Essentially, it amounts to proving that I can think of the tangent sheaf, since my tangent spaces are algebras, or Frobenius algebras. Then I can think of the tangent space as a sheaf of algebras or sheaf of rings. And then there is a construction in complex geometry called analytic spectrum. And so the first property amounts to proving that this analytic spectrum is a branched covering. Is a branched covering with branching locus exactly the caustic. So you have to do some more careful study of the geometry here, and that's how you prove one. But for the remaining ones are actually elementary. So 2 and 6 are elementary properties. So you can prove it directly from the definitions. Okay. And now with this preparation, now I can go to I can introduce now the main object. This is what is called given Tausar matrix. And here the terminology is not, I received many complaints from people in representation theory because our matrix is something in the theory of quantum groups, and it has nothing to do with the given Tausar matrix. So somehow you have to be careful with this terminology here. So here's the proposition that we want to prove. Suppose that you have a semi-simple point. then there exists a unique series, matrix valued series, plus where is a n by n matrix with entries whose entries are in their holomorphic functions in a neighborhood of the point t0. So there exists such an operator series such that this expression psi of t r of tz e to the u over z is a solution to the structure connection. Moreover, this unique solution automatically satisfies moreover R satisfies the symplectic condition. Equals 1. Again, the transposition here is the usual transposition of matrices. Okay, and I just want to sketch a little bit the proof of this. I just want to show the logic of the proof so that we can get a feeling of what this R matrix is, how it's constructed from the Frobenio structure. So first of all, so let me, so in flat coordinates, the structure connection or Dubrovin connection has the form D minus A Z inverse plus minus theta. Theta was the grading operator plus this is the operator of multiplication by the Euler vector field z to the minus 2 dz. So we want to prove that this expression psi r e to the u of z is so our condition for r is that this expression here psi r e to the u over z is annihilated by this operator, right? Now if we use proposition 1, we can compute the conjugation of this structure connection with psi. So using proposition 1, we can compute that psi inverse compose delta compose psi is equal to d plus psi inverse d psi, right? So this term comes when you compose the conjugate the de Rham differential. Then the conjugate of the A matrix was du, right? Plus the conjugate of theta I'll just denote by minus theta, I'll denote it with v, so I call it v. And then the conjugate of E was u, right? The diagonal matrix with entries canonical coordinates. Where I denote it with V, the matrix minus psi inverse theta psi. Okay, and then the claim is that so now what we want to, so the way we define R is we want that this operator R e to the U over Z to be annihilated by this connection operator. And when you write it down so you substitute and you write in the powers of Z, and then you find that so we find that RK satisfy the following system of equations. So the first type of differential equations are the differential of RK plus psi inverse d psi RK equals the commutator of du and RK plus 1. And the second type of equations are K RK plus U commutator RK plus 1 equals minus V times RK. So all these RK, psi, U, these are n by n matrices, right? So with matrix valued functions on our Frobenius manifold. And now the way you resolve these equations is by induction on L. By induction on L, we prove the following statement. We prove that there exists a unique sequence of matrices R1, R2, RL, such that the following three conditions are satisfied. The first one is that 1 and 2 hold for k between 0 and L minus 1. The second condition is that, so if you apply the Euler vector field to Rk, you get minus Rk. You get minus KRK. So Rk is the entries of the matrix Rk are homogeneous functions of degree minus k. That's what this property says. And the diagonal part of 2 holds for k equals L. So these are the three things that the three conditions that we want to satisfy, that I claim that they uniquely determine R1 up to RL. And let me just point out that the last condition, it looks like it will involve also RL plus 1, right? But if you look into 2, since U is a diagonal matrix, actually this commutator does not contribute to the diagonal part, right? So therefore, the diagonal part of equation 2, when k is L, does not depend on RL plus 1. So let me show you, I just want to show how we construct R1. So let me consider only the case L equals 1. And then the rest is analogous. So let's write equations 1 and 2 for k equals 0. They become, right, so this one k is 0. R0 is the identity, so this term disappears. So 1 becomes simply psi inverse d psi is equal to du commutator R1. Well, the second, well, 2 for k equals 0 would give you, so 2 for k equals 0. This term also disappears, so you have u, so you will get u commutator R1. Sorry, I want the diagonal part of 2. Yes, for k equals 0. So I will have u commutator R1 is equal to minus v. And now let us write it if I write the equations in terms of the entries of the matrices, then the first equation would give me, so the ij entry of this matrix psi inverse d psi is equal to differential ui minus differential uj times the ij entry of R1. And now we use the following observation, that flatness of the structure connection implies that differential of u times psi inverse d psi plus psi inverse d psi du is 0. Right? This is just the condition that del square is 0. And so in particular, this conjugate connection, its square is also 0. And if you take the coefficient in front of z to the minus 1, you get exactly what I wrote, right? So psi inverse d psi du plus du composed with psi inverse d psi is 0. And if we write this, the entries in this equation, the ij entry of this equation would give us that differential ui minus differential uj wedge product, the ij entry of this matrix is 0. And now we use some lemma, which is called de Rham lemma. De Rham lemma. So the lemma is the following general fact. So if you have if M is a complex manifold, any complex manifold, and you have a function, holomorphic function in the neighborhood of some point, such that the differential of f at that point is not 0, then the following sequence is exact. Omega denotes the sheaf of holomorphic forms on the complex manifold. And the index T0 means that I'm taking the germs of the sheaf at the point T0. And here is df, the wedge product by df. Right, so this is an exact sequence. It's an exact sequence of OMT circle modules. And this lemma is not hard to prove, simply because if you use the implicit function theorem, you can arrange a coordinate system in which f is one of the coordinate functions. In the case when f is one of the coordinate functions, this statement is obvious. So that's why we have this lemma. And now we apply our lemma for this function in these settings, right? So our function would be ui minus uj. So apply the lemma. The lemma for f equals ui minus uj, then it follows that psi inverse d psi, so the ij entry of psi inverse d psi could be written as differential ui minus differential uj, which times alpha ij for some holomorphic function. Right. And therefore, now we look at our equation, right? And we see that we can define R1ij to be this holomorphic function. Define ij. This is for I different than j. Right. Okay. So now let's look at the. I want to look at. So now I want to apply condition 2 in the case when k is well, L is 1, so k equals to 1. So I want to compare the diagonal entries in this equation 2 when k is 1. And then what we find is that we'll find a formula for R1II, right? So let me write it. So comparing diagonal entries in 2 for k equals 1, we get the following equality. So R1II is equal to minus sum p equals from 1 to n. Then you have VIP times R1PI. And now one can know, so now the next step is just to observe that, know that V transpose equals minus V. So this is a skew symmetric matrix. This follows from the skew symmetry of the grading operator. So therefore the diagonal entries of this matrix are 0. And then from this we see that our formula here, right? So this formula here does not involve entries of R1 that are on the diagonal. It involves only the non-diagonal entries of R1, which we already determined on the previous in the previous step. So therefore, R1II is determined in terms of non-diagonal entries. And now in order to complete the construction of R1, we have to check that one has to check that E of R1 is equal to minus R1, and that equation 2 holds with k equals 0. right? But this is just, I am not going to do this check here. And this completes the case of our inductive argument when L is 1. And then you continue in the same way. So it's nothing new happens when you make the inductive step. Maybe here I just want to make one remark that this matrix R1 that I just constructed from the Frobenius structure, it's very interesting because so Dubrovin proved that actually this matrix is a solution to some classical integrable system that has the form of what is called Euler top. So in principle, if you want to find an explicit formula for R1, it's equivalent to finding explicit solution of some classical integrable system, and that in general is very difficult. So in very few cases you can find explicit formulas for R1. Otherwise, the remaining matrices R2, R3, etc., they are given by some algebraic formulas involving R1. So in some sense, this R1 is the most interesting part of the R matrix. The rest are given by some algebraic expressions in terms of R1. Okay. So this is the part with the given Tausar matrix. If there's no questions, then let me, I would like to continue with the quantization formalism. Okay, so we will use certain quantization formalism to construct a differential operator from this matrix. And this differential operator will be used to define what is called total ancestor potential. So let me explain the quantization formalism. So this quantization formalism is really some linear algebra, so you can do it in great generality. So suppose that we have a finite dimensional vector space. Vector space equipped with a non-degenerate symmetric bilinear pairing. Let us denote with H the space of formal Lorentz series in Z inverse with coefficients in this finite dimensional vector space. And then we define the following skew symmetric form on H: omega f of Z, G of Z is equal to residual Z equals 0, f minus Z, G of Z, dZ. So this residual here simply means here we formally, so f of minus Z is a Lorentz series in Z inverse with coefficients in H, and the same is true for G. So you take the pairing of the coefficients, right, of these two series. You compute the pairing using the given non-degenerate bilinear form. And then the residual means that you have to take the coefficient in front of Z to the minus 1. So purely formally. And then these definitions turn this pair H and omega into a symplectic vector space. Symplectic vector space. Now let us fix dual basis phi I and phi upper J dual basis of H with respect to the pairing. So dual basis means that the pairing of phi I and phi j is delta ij. Now every so this would allow us to give a Darboux coordinate system on this symplectic vector space. So namely, if you have for any vector in H, any element of H could be written, could be decomposed in the following way: sum k from 0 to infinity, sum I equals from 1 to n. Then you have qki times phi I zk plus pki phi upper I minus z to the minus k minus 1. So these coefficients qki and pki, they are linear functions on H that they can be viewed so they can be viewed as coordinates on H. And I want to clarify this statement that so claim pki and qki are Darboux coordinates. Are Darboux coordinates on H. So let me explain this statement. I think that there is some elementary point here, but I want to spell it out because I think it's conceptually important. So we can think, so let us think of the vector space H as a complex, as a manifold. Then the linear structure allows us to identify, to trivialize the tangent bundle. So T of H is isomorphic to H times H. In other words, each tangent space is naturally identified with the vector space itself. Maybe I can recall this identification. So if you think of the tangent space as derivations from the germs of holomorphic functions to C, right? The tangent space could be viewed as such linear maps from OHA to C that are derivations. Then any vector here is going to define a derivation in the following way. So if you have a function, OH of A, then you associate, you take d epsilon of f of A plus epsilon v, and you compute it at epsilon equals 0. Right, so this way, every vector, this is just the derivative in the direction of the vector v. Right, and that's how we identify each tangent space with the vector space itself, and then the tangent bundle is just this product of H times H. And now if you use this identification, then we can define a symplectic form. So let me denote it with small omega. So now if V equals AF and W equals AG are two vectors in the tangent space, then we define omega V W to be capital omega of FG, right? And with this definition, the pair H omega is a symplectic manifold. Now note that in our identification, the vector field, the coordinate vector field ddqi is identified with phi I z to the k, and ddp ki is identified with phi upper I minus z to the minus k minus 1. So therefore, we can compute that omega of ddp ki ddq lj is equal to omega of phi I minus z minus k minus 1, then phi j z to the L. And then we see that this pairing is not 0. First of all, only if k is equal to L. And second, only if I is equal to j. So therefore, the form omega is exactly the sum of the pki, dq ki, sum over all k and I. So, and that's what this is the standard symplectic form. So that proves that p and q are Darboux coordinates. Okay. Now, if suppose that we have a linear map now, if A from H to H is a linear map, then this linear map determines naturally a vector field on H, namely we define the tangent vector at the point A would be minus A times applied to A, right? So this is an element of dA of H, right? Which is isomorphic to H. So this is a linear vector field. So let us give the following definition. If f from H to C is a holomorphic function, then there is a uniquely defined vector field, which we denote with xf on H omega. I write now omega next to H just to emphasize that I'm thinking of H as a manifold, such that the differential of f is equal to minus contraction of omega by xf. And in this case, we say that xf, so vector fields obtained in this way are called Hamiltonian. Hamiltonian vector field. So this is a definition and lemma definition, right? And then one can prove the following proposition. This vector field XA, that this linear vector field XA that I defined here, right? So this is the definition. This linear vector field XA is a Hamiltonian vector field if and only if if and only if the linear operator A is an infinitesimal symplectic transformation, which means that omega of A f g plus omega of f a g is 0. And moreover, the corresponding Hamiltonian is HA of A equals 1/2 omega of A. So this is some quadratic function on our on H, right? So now let us recall that this symplectic manifold has an underlying Poisson structure. Let us recall that H omega has a Poisson bracket. Defined on the sheaf of holomorphic functions. And actually, you can, it's given explicitly by the following formula: sum over all k and I, and then you have df dpki dq dg dqki minus df dqki dg dpki. And then one can prove easily the following proposition. Proposition 4. If A and B are infinitesimal symplectic transformations of well, the symplectic vector space H omega, then we have the following relations. The commutator of XA and XB is equal to X of AB. So in other words, we can think of the Lie algebra of infinitesimal symplectic transformation as the Lie algebra of linear vector fields on our manifold H. And also we have that the Poisson bracket of HA and HB is equal to H of the commutator of A and B. So therefore we can think also of this Lie algebra of infinitesimal symplectic transformations as the Poisson Lie algebra of quadratic Hamiltonians. Right? So this is what I wanted to explain. Right? So the proofs are straightforward, so I skip them. And let me give you some formula for H of A when A is a, so suppose that we have an infinitesimal symplectic transformation of the following type. It's a series. K equals from 1 to infinity, AKZ to the K. So AK is an endomorphism of H. So here this series operator, series A of Z, acts on curly H, on the symplectic vector space, simply by Z acts by multiplication, and AK acts by as it acts on the coefficients of the series. Right? So this series naturally defines a linear transformation of the symplectic vector space. Then one can prove that A is an infinitesimal symplectic transformation of H omega if and only if A transpose of minus Z plus A of Z is 0. And here the transposition here is with respect to the pairing. Now, for brevity, let me denote. So I want to suppose that we have some infinitesimal symplectic transformation. I just want to write down the formula for the corresponding Hamiltonian. Put Qk to be some I equals from 1 to n, Qki phi, and PL, maybe I could write it on the next page. PL equals sum j equals from 1 to n, PLJ Vj. You know, here, since Q and P can be told as linear functions on the symplectic vector space curly H, you can view these Qk and PL as functions from H, from curly H to the finite dimensional vector space H, right? Or you can just take these as formal definitions, Qk and PL. And then the formula for HA would take the form. It will be sum KL equals from 0 to infinity. Then you have 1/2 minus 1 to DL. Then we have AK plus L plus 1, PL PK, minus AKQL paired with PK plus L. So that's how the Hamiltonian would look. And now we can introduce the following quantization rules. Quantization rules. First, we define PKI. The quantization of PKI would be square root of H bar ddqki, and the quantization of QKI would be QKI divided by square root of H bar. And second, if you have any PQ monomial, then the quantization is defined this way. So first you can write the PQ monomial as a product of a Q monomial times a P monomial. And then you simply quantize in this order. So each QKI is replaced by this multiplication operator, right? And each PKI by the corresponding differential operator. Right. So for example,
sorry, I just want to ask one question. So
yes.
you now try to define normal ordering or something?
Yeah, this is normal ordering, right? Okay. So first, right? So yeah, so
this hat is the quantization. Okay, I see.
Yes.
Okay, thanks.
Yeah. So now I ideally would like to have to represent holomorphic functions on this symplectic manifold curly H with differential operators, and this is the rule. Right? So I think it's called canonical quantization in physics. So for example, actually these are the cases that will be relevant for us because we'll quantize only quadratic Hamiltonians. So this will give you H bar d square dqki dqlj. And finally, if A is an infinitesimal symplectic transformation of H omega, then we define the quantization of A would be just the quantization of the corresponding Hamiltonian HA, and if you consider the corresponding symplectic transformation, so Re to the A is a symplectic transformation, then we quantize this by simply exponential of the quantization of A. Right? So exponential of the quantization of HA. Right. So in our example, so if you have an infinitesimal symplectic transformation of this type, then the quantization will produce some second order differential operator. Right? Okay, and now I can come to the final part of the lecture. I can define the total ancestor potential. So suppose now that we have a semi-simple point, I'll denote it with S this time. This is a semi-simple point. We are going to apply quantization formalism for H, we are going to take the tangent space at the point S. Or you can think of this also as the space of flat vector fields. Vector fields defined in a neighborhood of S. Right, because each tangent vector, there is a unique way to make a parallel transport with respect to the Levi-Civita connection, and it will give you a flat vector field. And for the pairing, we'll take the Frobenius pairing. Frobenius pairing. Let me also keep using t equals t1, tn as flat coordinates, and u equals u1, un as canonical coordinates. And now there's a natural, if you fix flat coordinates, there's a natural choice of dual basis. Namely, you can call phi A to be just the flat vector field dDTA, right? And then phi upper A could be, you just take differential of TA, right? So this is element of T star M, and we identify cotangent and tangent bundle using the Frobenius pairing. So these are dual bases of H. So now the formal function that I want to define would be an element of a Fock space, and I'm going to denote this. So let us take H plus to be the subspace of polynomials in Z with coefficients in H. Right? So this is a subspace in H, and one can actually prove that this is a Lagrangian subspace. And I am going to take the Fock space. I will denote it with O hat OH plus minus Z. And I'm going to think of this Fock space as a completion of the ring of holomorphic functions on H plus, germs of holomorphic function on H plus at the point minus Z. So for some reason, not at the origin. And formally, this is just a ring of formal power series. So let me write it. Q0, Q1 plus 1, Q2, and etc. So here, Qk are just formal vector variables. So Qk1, Qkn. These are formal vector variables. And here by Q plus 1, more precisely Q1 plus 1, I mean Q1 1 plus 1, Q1 2, Q1 n. I probably didn't emphasize it enough, but here we assume that DDT1 is the unit vector field. So somehow we're shifting by 1 the coordinate corresponding to the unit vector field. Right. So shift in the unit direction. It looks strange at first sight, but actually many formulas in Gromov-Witten theory become more natural if you work with the ring of formal power series in somehow one of the variables is shifted by 1. So this is called dilaton shift. Okay, and then I can, so let me recall the definition of the Witten-Kuntzević tau function. So it corresponds, so this function is, we should think about a one-dimensional Frobenius manifold. But anyway, so this function is just a generating series, which I'll denote like this. Right. So it is exponential. Then you have sum over g and n from 0 to infinity, h bar to the g minus 1 divided by n factorial, and then integral mgn bar t of psi 1 t of psi n. So mgn bar is, you can think of it as the Gromov-Witten invariance of a point. which is the reason I put a point here. So yesterday I defined what is a psi class, so I'm not going to do it here. So here, with bold-face T of Z, I denote this formal series with coefficients T0 plus T1Z plus T2Z square plus etc. Right, so maybe I can write, so psi I is the first Chern class of this tautological line bundle Li. M bar Gn is just the moduli space in Gromov-Witten theory with target point, degree 0. And so let us, so this is, so here T0 and T1, T2, T0, T1, and etc. These are scalar variables, not vector variables. And now I want to define from this an element in our Fock space. So let us define, let us denote with bold-face Q of Z this series. Some A equals from 1 to n, QK A, phi A, Z to the K. So this is an element of H plus, right? So I want to define a function on H plus, formal function on H plus, and then our definition is this. Note that this product I from 1 to n, d point, then I take H bar times delta I, Q of Ui plus Z. So this is an element of our Fock space. Sorry, I think that I should put the hat over O. So these delta i's are the same that I used before, right? So delta I inverse was the Frobenius pairing of DDUI and DDUI. And here, know that I could think, so here I can think of phi A also as a flat vector field, right? And therefore it makes sense to differentiate the function ui. The canonical coordinate is a function on our Frobenius manifold. So therefore this expression here produces a formal, it's not a vector expression, right? So it becomes a scalar expression. So it makes sense to substitute it in the Witten-Kontsevich tau function. Maybe I can write, so this Q of Ui plus Z could be written, it simply means that I substitute in the Witten-Kontsevich function, Tk is substituted with delta K1 plus Qk of Ui, which in more details it's written as sum A from 1 to n, Qka, dui dta. Right? So this function is defined this way, and clearly you can check that it's a formal series in Q1, 1 plus 1, and the remaining Q variables are not shifted. Right? So that's the claim here. Okay, and then the total ancestor potential. Total ancestor potential of the Frobenius structure. So I'll denote it with a T of H bar Q. It is defined by, well, you quantize this symplectic transformation, psi of T R of Tz times psi of T inverse. Right, so this expression could be viewed as a symplectic transformation of our symplectic vector space, so we can quantize it in the way that I explained. And then you apply the resulting differential operator to this product of Witten-Kuntzević tau functions. Right. And maybe I make now one remark, or maybe several remarks. How much time? I have 8 minutes left. Okay, so exactly as much as I need, I think. So remarks. So the first remark is that one can check that the total ancestor potential has the form G belongs to the sum over all integers, then sum over all pairs, and then you have some coefficient here, right, which is some function in T, h bar G minus 1, then you have tk1 a1, tkr ar, right, so it's a formal power series of this type. And now I want to say something about the coefficients here. So where I denote it with tka, just these variables qk a plus delta k 1 delta a1. So if you want to write the generating function as a power series in the non-shifted variables, then I usually use t. And if I use q, it means that it's a formal power series in the shifted with the dilaton shift incorporated. Then one can show that that these coefficients, if you write them as a as coefficients of a, if I add to the coefficient this expression, dTA, dTAR, then, so you see, my definition of the total ancestor potential involved the choice of a flat coordinate system. So now I want to give some kind of an intrinsic coordinate independent interpretation of the total ancestor potential. And in order to do this, then you have to think of these coefficients as the coefficients of symmetric differentials. So this expression extends to a holomorphic R form on M minus K. Yeah, so this is the first remark. So if you want to think of the total ancestor potential globally, then that's the intrinsic interpretation. That's how they transform. So these coefficients, when you change the flat coordinates from one to another flat coordinate system, they'll transform as the holomorphic R forms transform when you change the coordinates. And the second remark is that one can prove that one can compute the differential equation with respect to the flat vector fields. So one can check that this total ancestor potential satisfies the following differential equation. You take Z inverse AK minus df1 dtk, and then you apply it to AT of H bar Q, where this function f1 of t, it's is defined in terms of the R1 matrix, the trace of R1 of t du plus 1 over 48 sum I equals from 1 to n d delta I divided by delta I, and it is called genus 1 potential. 1 potential. And in Dubrovin's work, it's called also G function. G function. And the operator AK, this is just the multiplication by the flat vector field dtk, right? So one can check that this expression here, Z inverse and this linear operator AK, this is an infinitesimal symplectic transformation, so you can quantize it. So it will give you some differential operator. And this is the differential equation satisfied by the total ancestor potential with respect to the parameters, the coordinate, the flat coordinates T. Okay, and finally one can define what is called total descendant potential. Total descendant potential. And to define the total descendant potential, we need to fix a calibration. So suppose M is a calibrated semi-simple Frobenius manifold. Then we define the total descendant potential by this formula, e to the f1 of t. So the calibration is also a symplectic transformation, so you can quantize it. Actually, we quantize the inverse of the calibration, and you apply to the total ancestor potential. And one can check that now however, the total descendant potential belongs to a different Fock space, not to the same one. So one can check that when you apply this differential operator, you obtain something that belongs to this Fock space, H plus, and then you take the completion of holomorphic functions at the point t minus z. Right, so this is the following space of a formal power series: Q0 minus t, Q1 plus 1, Q2, and etc. By the way, here one can check that if you differentiate formally the total descendant potential with respect to t, you'll get 0. So d is actually independent of the choice of a semi-simple point that you choose. But independent, but not quite, right? Because you see, it belongs to this space, right? So here there is a dependence in the Fock space. And you see what happens is, for example, I can give you a very simple example just to get some idea what's going on. So for example, if you have the function 1 over Q0, if you want to write it as a power series, the way to do it is you write it as, you write this as t plus Q0 minus t, then 1 over t, and you have 1 divided by 1. You expand it as a geometric series now, right? And then this becomes 1 over t, and then you have sum k from 0 to infinity, and you have minus 1 to the k, q0 minus t to the k divided by t to the k, right? So in that sense, here we have some power series that, well, formally, if you differentiate with respect to t, you get 0, but you know, it's not quite independent of t. So, but what we can say is that if you write the logarithm of the total descendant potential as sum g equals from 0 to infinity fg of q h bar to the g minus 1, then each of these potentials, if the genus G potential, is a holomorphic function on M minus the caustic. And then you have Q1 plus 1, Q2, etc. So in principle, in general, if you have an arbitrarily calibrated semi-simple Frobenius manifold, the total descendant potential will be a formal power series in Q1 plus 1, Q2, etc., whose coefficients are analytic functions on the complement of the caustic, but in principle, they could have singularities along the caustic. Right. And there are examples where indeed there are singularities. Okay, so I'll finish today here. And so continue tomorrow.
Thank you very much. Are there questions? I have one question, a very elementary one again.
Yes.
You have a simplex condition for S and R, right? You in the previous lecture. How does it have to do with this simplex form of Kali H and disquantization?
So this is this. I gave some condition when is for it was here.
Yeah.
So this is the condition that A is an infinitesimal symplectic transformation.
Yeah.
Now, okay, so maybe I can write it in, here. So similarly, you can check that. So suppose that you have. Let's do it for R. It's the same for Z. Suppose that you have R, which equals 1 plus R1Z plus R2Z square, etc. Then symplectic transformation. Symplectic. This is equivalent to omega A, sorry, not A, but R of Z, F of Z, G of, sorry, not R of Z, G of Z equals omega of F, G, right? So it preserves the symplectic form. Yeah. And now if you recall the definition, this would involve here R of minus Z, so it will involve the pairing of R minus Z, F minus Z, and then R of Z, G of Z, right? So it's some residual here. And now I can use the transposition to rewrite this as F of minus Z, R of minus Z transposed, F R of Z, G of Z, which is, this is the same as the symplectic form of F, R transpose minus Z, R of Z, G. And since the symplectic form is non-degenerate, the only way that this expression equals this is if this is 1. And that's exactly the symplectic condition that I used.
I see. Okay. Let's see. Okay. I see. I see. Okay. And then you define the ancestor potential by using R matrix and also with the Kontsevich tau function, right?
Right. So I take a product of Witten Kunzage tau functions, but somehow each copy is somehow modified. The modification depends on this idempotence for the Frobenius algebra, right? So somehow you have to use the canonical coordinates here.
Oh, I see. And how does it have to do with this connection nabla? Does it satisfy differential equation or something?
Yes, the differential equation that follows from the connection is the one that I listed here in 2. So this is how you prove.
Oh, I see.
Because the R matrix the R matrix that enters in this definition, here this operator satisfies some differential equation. Namely, I conjugated nabla with psi, and therefore this conjugated nabla would give you the differential equations for this operator, right? So therefore this somehow it's some kind of a quantization of this. Not quite the quantization, but somehow the symplectic transformation satisfies differential equations, and then the quantization of the symplectic transformation also satisfies some differential equation.
I see.
Right.
Okay, thank you very much. Are there any other questions from audience? Maybe your lecture is too clear. So everything's transparent.
I think that this means two things. Either there are two types of people: the one who know the thing in advance, so they don't need any explanation, and the other is that the one who couldn't.
No. I'm totally.
No. It's. I think it's kind of if it's the first time you see this, I think I make many small statements without proof. So if you don't sit down and think about it, it's very hard probably to.
No, even I'm a beginner. It's very, very transparent and clear. I learned a lot.
Good. That's good. One thing that I didn't include in this lecture, and probably it was going to be good to say it, is that to return to the example of Gromov-Witten theory, because then this total descendant and total ancestor potential are they have geometric significance. There are some generating functions of Gromov-Witten invariants.
Yeah, that's true. Yeah.
So somehow here in this abstract theory of semi-simple Frobenius manifolds, we take this formula just as a definition, but in Gromov-Witten theory, it was a hard work to prove these formulas.
I see. And okay, but it's maybe I can ask one more question. So how can you relate it to some mirror symmetry and so on? This is, I mean, if you consider Gromov-Witten theory, this is A model side, and can you construct similar story in B model side, but maybe using lambda Ginzburg?
Actually, for me, mirror symmetry is genus 0, and therefore. I mentioned this in the work in the beginning when I talked about Saito's work in quantum homology. So you see, mirror symmetry is this phenomena that sometimes these two constructions, one that comes from quantum cohomology and the other one that comes from Saito's theory of primitive forms and flat structures, sometimes these two coincide, and this is called mirror symmetry.
Okay.
And there is a conjecture actually that if the quantum cohomology is you can find a flat structure in the sense of psi2, which coincides with the quantum cohomology.
I see.
And that would be this site of Kyoji site would be the B site. You know, and somehow here in quantum cohomology, the flat structure is very easy to define. But the multiplication is very difficult. And on this B site is the other way around. So here, the flat structure is very difficult to define and the multiplication is trivial. And I guess that's why Saito called it a flat structure, because the multiplication in his picture was just very easy. But the flat structure was something that nobody knew at the time, so it was something hard to see.
I see.
Right, so in some sense, mirror symmetry, for me, it means that this Frobenius structure that defines the total ancestor potential and descendant potential has two different interpretations, right?
Yeah.
Right. But there is another work of C. Lee that he tries to define directly higher genus invariants on the B side without the reconstruction, the genus zero reconstruction. So with Costello, they have a model for Calabi-Yau manifolds. And so probably there is some higher genus version which somehow it's compatible with this story here.
I see.
But I think it's this is somehow it's not well understood yet. The higher genus.
I see. So this ancestor, ancestor and descendant. So total descendant potential is more or less conservative within tau function.
It is it's some kind of in some sense you in this case in the semi-simple case since the Frobenius algebra decomposes into one-dimensional Frobenius algebras, this somehow this property is inherited by this total ancestor potential. So somehow up to this quantization of symplectic transformation, the total ancestor potential also decomposes as product of.
Okay. But you how does descendant potential related to tau function?
The expectation is that the descendant potential is a tau function.
Oh, okay. So, I see.
And this would be our strategy actually. We know that these the Witten-Kuntsevich functions are tau functions of KdV. So in some sense, we would like to take n copies of the KdV hierarchy and obtain somehow from it, we want to construct Hirota quadratic equations for the total ancestor potential. Right? That's the expectation. So it's right. It's not easy to formally you can conjugate, right? So you can obtain some Hirota quadratic equations for the total ancestor potential just by conjugation. But it's very hard to relate these Hirota quadratic equations to an integrable hierarchy.
I see.
Or yes, I don't have a good answer. It looks like if you conjugate just by this operator by R, you should be able to get some kind of Hirota quadratic equations. But it's not somehow I'll try to explain in my lectures. I think that somehow the whole point is to try to write Hirota quadratic equations for the total descendant potential. That's not easy, right? So I think it's easy to write Hirota quadratic equations for the total ancestor potential. But then if you want to transfer them to the total descendant potential, then there is a problem. By the way, I can compare it if for people who are familiar with the Einar-Turantian recursion, something similar happens that if you take so this function Witten-Kuntsevich tau function is an eigenvector for is a highest weight vector for the Virasoro algebra, and this condition is equivalent to the fact that the correlators of the Witten-Kuntsevich tau function satisfy a topological recursion relations, the Einar-Turantian recursion. And if you conjugate this each Virasoro constraint, you'll get n copies of Virasoro constraints for the total ancestor potential. And they give you some kind of a recursion relations for the correlators of the total ancestor potential, which is called local topological recursion.
I see.
But it's not global. So somehow if you want to make it global, it's not so obvious that you can do it.
I see. Any other question from audience? Okay, if not, let's thank the Todor.
Okay.
I will stop recording.